Previously, you probably learned about convergence of sequences. Now we've got to talk about convergence of series. If you keep adding up numbers forever, do they converge to something? So to talk about this in a more precise way, it's helpful to define a partial sum. And you've probably seen this before as well, but the partial sum, we'll denote it as S capital N, and it's just the sum of the first n terms, right? So it's not the infinite sequence, it's just the first n terms. And what we say is that the series converges if the sequence of partial sums converges. So that means you look at the first term, then you look at the sum of the first two terms, then you look at the sum of the first three terms, then you look at the sum of the first four terms, and you keep going forever, and if those sums settle down to something, that is, if the limit as n goes to infinity of s sub n equals s, where s is a finite number, we say the series converges. So here's an example, 1 plus 1/2 plus 1/4, and so on. You might recognize that as a geometric series. You can actually compute what the sum is, and since the sum is equal to 2, since that exists, we say that the series converges. Here we have 1 plus 2 plus 3 plus 4, and so on. This diverges, and for now, we're not going to prove that, but hopefully it's intuitive to you. There's different ways of proving something converges, and there's not just one simple formula that will always tell you for any kind of series. So sometimes it takes some work, but we can start talking about a couple of just brief, useful convergence properties. And here in this section, for my summations, I haven't written sum from 1 to infinity because it just gets cumbersome, so just know that it's implied. I'm just writing my sigmas without indices or limits on them. So if we have two different series that converge, then linear combinations of them also converge. That means if sum of an goes to something and sum of bn goes to something, then for constants k1 and k2, the sum of k1an plus k2bn converges, and it converges to what you get if you just separate the sums and pull those constants out in front. It's just algebra, and hopefully it's intuitive, but just know that that's a rule that you can use. Also, changing a finite number of terms in a series won't change whether or not it converges or diverges. If it converges, it'll certainly change what it converges to. The number that it converges to might change. But if you just pick 10 terms or 20 terms or 1,000,000 terms and change them, so long as you don't change every term, if the original series converged, your changed one will as well. Here's something that's really convenient. The limit as n goes to infinity of the nth term must equal 0 in order for a series to converge. That doesn't guarantee the convergence. So we say it's necessary, but doesn't guarantee. So here's an example. 3 plus 2 plus 1 plus 1 plus 1 plus 1 plus 1 forever. Now we can say that diverges because of this property, right? So as n goes to infinity, we're not adding on zeros. We're adding on something non-zero, so it diverges. Here, 1 plus 1/2 plus 1/4 plus 1/8, and so on. If we just use this rule here, the nth term does approach 0, so what this tells us is that this series might converge. And of course, if we recognize it as a geometric series, we know that it does converge. This property doesn't tell you that it converges, it just tells you that it might. Here, 1 plus 1/2 plus 1/3 plus 1/4, again the nth term approaches 0, so this property tells us that it might converge. However, this particular one, which is called the harmonic series, turns out not to converge. Finally, if you have a series that diverges, multiplying it by a non-zero constant doesn't change anything, it still diverges. Okay, thanks for listening.